Thank you. All right, so yeah, I'll talk about local global compatibility and monodromy. Let's take L to be a CM field. Some isomorphism of QL bar with C for some prime L, and pi, cuspidal automorphic representation of GLN of the adels of L, such that pi is conjugate self-dual, and pi infinity is cohomological for some irreducible algebraic representation of GLN. Let RL of pi be the Galois, so the global Galois representation associated to pi, RL of pi from Galois group of L bar over L into GLN of QL bar. Then I want to talk about the following theorem. So let's take Y to be a place of L above a place P, which is distinct, so above a prime P, which is distinct from L. Then we have the following isomorphism of Wedelin representations. So on one hand, the Wedelin representation of RL of pi restricted to the Galois group at the place Y. And we Frobenius semi-simplify it, and that's the same as IL inverse of ln ly of pi y, and we don't need to Frobenius. So this is the local Langlands correspondence, and I'm using the geometric normalization. Okay, this theorem was previously known in almost all cases, so let me summarize. Oh, sorry. Yes. Huh. Okay. Sorry. Okay, so known for n odd, for n even, and pi slightly regular in the terminology of Shin. Or when pi is square integrable at a finite place. And in general, it's known up to semi-simplification. So that means that it's an isomorphism of representations of the Weil group, but without the knowing the monodromy, that the monodromy operators match up. And this was done in many steps by lots of people. I hope I don't forget anything. So Harris-Taylor, Taylor-Yoshida, Shin, and Chenevier-Harris. Yes, that I was planning to mention. Yes. Okay. Yes. And all right. we'll try to, well, we'll extend this to Frobenius semi-simplification in the case when n is even. Okay. So just to mention the part of the difficulty when n is even arises from the fact that you can't find a unitary group which has signature 1, n minus 1 at one infinite place, 0, n at all other infinite places, and is quasi-split at all finite places. What we'll do is so we have to prove, I guess, two things. So call them A. We have to prove that the Wedelin representation associated to RL of pi, restricted to this place, and Frobenius semi-simplified is pure, and that would completely determine what the monodromy operator is. And another thing is, well, to prove the same thing for Ln Ly of pi y. And this would follow from the Ramanujan-Peterson conjecture. For pi, which states that pi y is tempered. And this was proved in the unramified case by Clausel. Okay. And both A and B follow from studying the cohomology of a Shimura variety, which realizes not quite this representation, but this representation tensored with itself. And this Shimura variety is associated to a unitary group, which at infinity has signature one n minus 1. Well, so it looks like u1 n minus 1 cross u1 n minus 1 cross u0 n to the d minus 2. So at two places it's 1 n minus 1. At all the others it's 0 n. All right. So I'm going to introduce some notation, I guess. Let's see. Although maybe it's better to write it here, so just to have it. E will be a quadratic imaginary field. F1, in which P splits. So P is equal to U times U conjugate. F1 will be a totally real field. We take F prime to be F1 E, and we pick a place P of F prime above U. So F prime and P will basically play the part of L and Y. But I guess one thing I forgot to mention here is that we will work with a Shimura variety of Iwahori level, because what we're trying to prove is a purity result, and that's preserved when you pass to finite extensions of fields. So we can assume that we're in a situation where the representation at P has a, well, an Iwahori fixed vector. Okay, so that's why, you know, we're working in general with something like this. All right, F2 over F1 will be a totally real quadratic extension such that F is F2E and P splits as P1 times P2 in F. Okay. And we also pick some embeddings of F into the complex number, 2 of them, such that tau 2 is equal to tau 1 composed with sigma, where sigma in the Galois group of F over F prime takes P1 to P2. And these would be kind of the 2 places where our unitary group has signature 1 and minus 1. So starting with F, F to the n as a vector space, and we find some pairing, we get a unitary group, G, well, it's a unitary similitude group. Let's say it's an algebraic group over Q, which has signature 1 and minus 1 at tau I for I equals 1, 2, and has signature 0, n at tau, well, other tau, such that tau restricted to E is equal to, so since, so tau 2 restricted to E is the same as tau 1 restricted to E, and we just call it tau sub E. So all other embeddings, which on E just give you tau E. And also such that G is quasi-split at all finite places. So this is at infinity and quasi-split at all finite places. And such a group exists because the global invariant is ND plus 2, ND over 2 plus 2, and we can always ensure that this is even. Okay, and so associated to this unitary group, we have a Shimura variety. Say for some compact open U, we take XU to be the Shimura variety of level U. This is going to be defined over F prime. So if you write the Shimura datum, F prime will turn out to be the reflex field. Okay, so we have this Shimura variety over F prime. It's proper, smooth, has dimension 2n minus 2. Yes? Oh, D is going to be the degree of F2, I think, over Q. So that's even to begin with. But yeah. Okay. So we have this. It's a moduli space for abelian varieties with polarization, an action of F, a U-level structure. So everything is as usual. And they have to satisfy, well, the usual conditions. And in the cohomology of this, so HI, oh, I guess I should say, we take some C to be an irreducible algebraic representation of G over QL bar. This defines a local system LC on the inverse system of Shimura varieties. Okay, and we can look at, in the limit, we look at the cohomology of HI. I'm just going to note it X, LC. And this has an action of the Galois group of F prime over F, F prime bar over F prime. And it decomposes as direct sum over irreducible admissible representations of the finite G of the finite Adels of pi tensored with Ri C lambda of pi. So this is where we find a Galois representation. And this will be the one that realizes RL of pi tensored with itself. And at the same time, this can be obtained as a part of the cohomology of the universal abelian variety over X with coefficients in QL bar twisted some number of times. So the representation Xc defines some integers mxc and txc. And anyway, this cohomology can be obtained as part of this. So if we want to understand the Galois representation, we might as well study the cohomology of this. And the universal, so AU, let's say, is the universal abelian variety over XU. Then it's smooth over XU. So if we want to understand its cohomology, first we need to figure out what the geometry looks like. And since it's smooth over XU, it's enough to understand the geometry of XU. OK, so we're going to work with an integral model of XU. Sorry. First, the other board. All right. Is it high enough or no? Oh, well. So we're going to work with an integral model over OK, where K is, well, f prime localized at P, which we identify with f localized at P1, and it's isomorphic via sigma with f localized at P2. OK, pi will be a uniformizer of OK, and the residue field is F. So this integral model is sort of defined in a standard way. But the one, I guess, important thing is that there's, well, Kottwitz's determinant condition that must be satisfied by abelian varieties, which solve this moduli problem, will imply whenever A is an abelian variety which satisfies the moduli problem, that the p-divisible group of A at pi for I equals 1, 2 is a one-dimensional compatible Barsotti-Tate OK module. OK. And at primes, at the other primes, which are above the place U, the p-divisible group is indetal. So basically, I guess locally, this Shimura variety deforms, well, the p-divisible group, but only these two parts of the p-divisible group have any interesting deformation theory. I said that we will work with Iwahori level structure. So let's say XU is the Shimura variety for with Iwahori level structure. Then it will be a moduli space for chains of isogenies so let's take this to be G sub I. it'll be a moduli space for chains of isogeny Ci, which takes GI, say that's the 0th, to GI1, and so on, to GIN, which is GI mod the pi torsion. And this happens for I equals 1, 2. OK, so basically we can compute the completed strict local rings of the Iwahori level Shimura variety just by, I guess, computing the deformation rings of this. And even further, we can figure out something about the local geometry of XU. So locally, XU looks, is étal over X R sub S, which is spec of OK joined X1 through Xn, Y1 through Yn, and modded out by X1 times XR minus pi, and Y1 times Ys minus pi. OK, and this is a product of semi-stable schemes.
Excuse me, what do you mean by locally?
Zariski locally. OK. Let's see. And more than that, the special fiber of this Iwahori level Shimura variety has a stratification. So let's take Y to be the special fiber of XU. I'm not going to write U. Then Y is the union of Y, I, J, where this corresponds to, so it's the closed subscheme where the jth isogeny in Ci has connected kernel. So for I equals 1, 2. And then we can define Y sub st whenever S and T are subsets of 1 through n as the intersection of, well, the corresponding subschemes for S and Y1 and T and Y2. So intersection over I in S, Y1I, and intersection over I in T, Y2, well, J and T, Y2J. OK, and this is proper and smooth and has dimension, so over OK, and has dimension, over F. 2n minus cardinality of S minus the cardinality of T. And we can even consider the disjoint union of such strata for when we keep the cardinality of S and T constant. And I'm going to call that Y set L1, L2. So we're taking the disjoint union of YST, where the cardinality of S is L1, cardinality of T is L2. And even I'll denote A L1, L2, the projection of this onto the special fiber. All right. So we really want to understand sort of the, I guess, the cohomology of the abelian variety. So the universal abelian variety special fiber of it over Y has the same stratification. OK, and so I'm going to call AMCU over OK. I'm going to call this A. All right. And so we're interested in H upper star of A K bar with coefficients in QL bar. That's isomorphic to the hypercohomology of A F bar with coefficients in R psi QL bar, where this is the complex of nearby cycles. So this, okay, so let's see. So in general, if lambda is either a torsion sheaf or ZL, QL, QL bar, we can define the complex of nearby cycles. I'm going to use the definition in SGA 713. But I mean, it's a definition that goes through OK bar rather than maybe the one that most people have seen that goes through OK unramified. But they're equivalent. One thing about this that I want to say is that it's an object in, so I'll write it and then I'll explain what. Y F bar tensor over F with K lambda. So it's basically an object in the bounded derived category of constructible sheaves of lambda modules on YF bar, which has an action of the Galois group of K, and that action is compatible with the action of the Galois group of F on YF bar. Okay, so this is what we're working with, and the monodromy operator N on H star of, say, A, just A, K bar, QL bar, is actually induced from an action of, from a monodromy operator N on this complex. Okay, well, I should write QL bar. And this isn't obviously defined, but it is possible to, well, in our case, you can show that this is well defined. Okay, and we want to understand, well, if we want to understand the action, yes?
Sorry, a very stupid question, but what is the K?
K is characteristic 0, yes.
So why did it tensor over F with K?
Oh, it's a notation. So this is a product of toposes. And, but in this case, what it's equivalent to is saying that there are sheaves here with an action of this Galois group, which is compatible with. That's because the F and K, as if you look at sheaves there, it's basically just a representation of the Galois group, I think. But yeah, sorry, yes?
Just another question. I don't think it's important, but the local system has disappeared at this point.
Yes, because we're, so eventually we're interested in the cohomology with coefficients in the local system, but that's just a piece of the cohomology of the abelian variety, or, well, something smooth with coefficients in QL bars, something smooth over that. And so we're just going to work with QL bar, and at the end, once we understand this, we're going to go back to using the local system. Okay, so, and the goal will be to understand the monodromy filtration of N on this complex. So, okay, and by monodromy filtration, I mean the filtration that you get by convolution. So you convolve the kernel filtration of N and the image filtration. And since I'm talking of filtrations, I should say that this is a minus dimension of A shifted perverse sheaf. So that means that, well, once you shift it to the right this many times, it will live in an abelian subcategory of this category. So if we have an action of n, we can talk about the kernel, the image, kernel filtration, image filtration, and so on. OK. And so the monodromy filtration, the graded pieces of the monodromy filtrations are, where this is the kernel filtration, and this comes from the image filtration. So it's induced by the image filtration on the graded pieces of the kernel filtration. OK, so we want to understand this, and I'll state a theorem that, well, gives some way of getting our hands on this, and then I'll explain how we get it. Oh, boy. There are GK equivariant spectral sequences so E1 R m minus R, where the term is equal to sum P minus Q equals R, HM A F bar, GRQ, GRP, ARP psi QL bar. This converges to HM AF bar ARP psi QL bar. So this is just whenever you have a filtration, you can associate to it a spectral sequence, and that's all it is. And then there's another spectral sequence, E1 prime, K plus 1, M minus K minus 1, which basically computes these terms. So here, the term is equal to a sum from I equals 1, P plus Q, H. OK, this doesn't look so nice, but it simplifies in the end. A F bar, K plus I, K plus and with coefficients in QL bar, twisted, minus K plus P minus 1 times. And this converges to that term. So HM AF bar R GRQ GRP. OK. And here, by this, I mean the corresponding strata. So we define this for the Shimura variety, and we take the corresponding part that has to do with the abelian variety. OK. So I guess I can briefly explain how we get this. It's kind of a sort of a step towards generalizing the weight spectral sequence, the Rappaport-Zink weight spectral sequence that works for a semi-stable scheme. In this case, we're dealing with a scheme that is that is locally étale over a product of semi-stable schemes. So I'll just mention what the key ingredients in proving that theorem are. Well, so one thing is that A over OK can be endowed with something called a log structure, which is a sheaf of monoids on A, such that AM over OK with a standard log structure N is log smooth. So log smooth is a notion that was kind of derived to generalize the notion of semi-stable. And it's, in a way, the same as smooth for log schemes. It's log smooth in the category of log schemes. It's something that's preserved under composition and base change, and that you can check at all locally. So given the description we have of the geometry, this is log smooth. And in this case, Nakayama has a computation of the sheaves of nearby cycles on A. So, well, we derive it from Nakayama. R k psi lambda twisted k times is isomorphic to the kth exterior power that we get from this sheaf of monoids. We make it into a sheaf of groups. We throw away some things and the part that comes from n, and then we tensor over z with lambda. And moreover, the action of inertia on these sheaves is trivial. OK, so that doesn't quite tell you how inertia acts on the whole complex, but at least it tells you how it acts on the cohomology sheaves. Another thing, so this is follows from Nakayama's work, is that when x1 and x2 are semi-stable schemes over OK, we have r psi lambda on x1, exterior tensor product, and derived is isomorphic to r psi lambda x1 tensor over OK with x2. And this was proved by Illuzy. And this is together with the inertial action, so with the action of monodromy. OK, so the isomorphism is compatible. And the third ingredient is Saito's construction of the weight spectral sequence for a semi-stable scheme. So let's say for x1 over OK. And I'll talk about that because what I'm doing is really just generalizing that method. Ow. So from 1, for instance, even in the case of semi-stable, as well as in our case, you can get a resolution of this sheaf, except that we put it in degree k rather than in degree 0, and we get a resolution of it by the following complex. So it's isomorphic to the following complex, where each of these, so AK is just the projection of yk onto y, well, y1. So y1 is x1 special fiber. And it's a union, disjoint union of strata that you get by intersecting k smooth divisors. Yes, we're only talking about one semi-stable scheme, just briefly. Cardinality of S is equal to k. All right, so when you have such a resolution, it turns out that these are shifted perverse sheaves. They're all shifted by the same amount. So you can see that this is, well, this is an extension of shifted perverse sheaves. It's also a shifted perverse sheaf. It's shifted by minus dimension of x1. So basically, these pieces are the graded pieces of a filtration on the complex. That filtration is called the canonical filtration. And, well, since they're the graded pieces of the filtration, and also, in this case as well, inertia acts trivially on the sheaves. So that means basically that, say we take T to be a generator of the pro-L part of tame inertia. That's the only one that has any meaningful action. Then T minus 1 sends fill K to fill K minus 1. And so T minus 1 induces a map from RK to RK minus 1. So I'll denote by mu to be T minus 1. And this induces a map mu bar from RK shifted to RK minus 1 shifted. And thing is, you can actually describe that map mu bar as an explicit map of complexes when you replace this with this complex. So you can study the map mu bar pretty explicitly. So in the semi-stable case, this map mu bar turns out to be an injection, and so these pieces are exactly the graded pieces of the kernel filtration. And then to get to the image filtration, well, you just look at the image of mu bar on here, and mu bar squared, and so on. Okay, so this is how it works out in the semi-stable case, and so you can compute exactly what the graded pieces of the monodromy filtration are, and that's how you get the weight spectral sequence. All right, so in my case, I can pretty much go as far as this. So let me explain that. Oh, no, this first. So in our case, from 1, we get a resolution of RK psi lambda minus k in terms of a L1, L2 star lambda twisted minus k times and put in degree L1 plus L2. Okay, and again, the action of inertia is trivial. These are going to be perverse sheaves shifted in the right dimension. So these are going to be perverse sheaves. Again, they're going to be the graded pieces of the canonical filtration. Of the whole complex. And so we will get an induced map if we denote again mu by t minus 1. We're going to get an induced map from the kth piece to the k minus first piece. And moreover, using 2 and 3, we can define a global map of complexes with these terms, which agrees with mu bar. And we can show that they agree by checking locally. So we can determine mu bar as a map of complexes. And locally, it agrees with mu 1 bar tensor 1 plus 1 tensor mu2 bar, where mu1 bar and mu2 bar are the maps defined for semi-stable schemes x1 and x2. So this is just locally where this, where the, I guess, scheme we're working with is étale over a product. Okay.
Are these maps defined geometrically because it's the same number of intersections in different degrees in the different?
Yeah, I mean, it only takes something like this to something that's the same, except it's twisted fewer times. So that's all it really does. It doesn't mix L1, L2 with something else. Okay. And so once we have something like this, basically, whatever this canonical filtration is, it induces a filtration on the graded pieces of the monodromy filtration. And using the explicit description of this map, we can compute the graded pieces of that filtration. So that's why we get two spectral sequences. So we can recover the graded pieces of filtration. Oh, God. Induced on GRQ, GRP, ARP psi lambda by the canonical filtration. And for that, we basically need to compute the kernel of the map mu bar, the image of the map mu bar, and the higher analogs. So there's one tricky point here, which is that you want to make sure that if you compute the kernel of mu bar, that actually doesn't compute anything extra, that everything comes from the kernel of mu. So mu bar, if something's in the kernel of mu bar, it may mean that it's in fil k and it gets sent to fil k minus 2. And you want to make sure that mu sends it from fil k to 0. So have to check that the kernel of mu surjects onto the kernel of mu bar. But that can be done, and the analogs of that for image and higher powers also. Okay, so basically from computing these, that's how you get the second spectral sequence. And the first spectral sequence is standard. All right, so now I have some time left, so I want to tell you how to use that spectral sequence to get anything interesting in the case that we care about. So what we care about is applying whatever spectral sequence we have to the cohomology of some universal abelian variety over a Aniwahori level Shimura variety. Now at this point, I'm going to rewrite everything in terms of x and y and the various strata and the coefficient system ELC rather than QL bar. So we want to apply the theorem to compute the pi 1 infinity part of h x ELC, basically. So the automorphic representation that we start with is pi. Maybe you base change it, then you have to add a GL1 part to it, you get a pi 1. And that's what you try to recover. So basically then in the spectral sequence, the terms will be, and say I can base change at all finite places except p, h star of, let's see, sorry. Well, let's say hj of yst ELC, and we're taking the pi 1 away from some finite set of primes containing infinity. And so this is what we want the terms in the sort of E prime spectral sequence to be. And we have the following proposition. This turns out to be equal to 0 unless j is equal to 2n minus the cardinality of s minus the cardinality of t. So basically, the cohomology of the pi part of the cohomology of this stratum vanishes outside the middle dimension. So in the spectral sequence E prime, most of the terms are 0. E prime k plus 1 m minus k minus 1 turns out to be equal to 0. So I should say rewrite in terms of x. So h, x, elk c, rather than h of a and ql bar. This is equal to 0 unless m is equal to 2n minus 2. So the spectral sequence E prime is concentrated on a diagonal. So in particular, it degenerates at E1 prime. Great. And then the terms of the second spectral sequence, E r m minus r, also are equal to 0 unless m is equal to 2n minus 2. So the second spectral sequence is also concentrated on a diagonal, and so it degenerates at E1. Now, the second one we got from the monodromy filtration. If it degenerates at E1, it means that sort of the monodromy operator n induces all the isomorphisms that we want it to induce in order to show that it's pure. And another thing to check is that I guess the pieces are strictly pure of the right weight. So ER 2n minus 2 minus r is strictly pure of weight 2n minus 3 plus r plus mc minus 2tc. And this you get by looking at E prime and seeing that all the terms that give you one of this are pure of the same weight. It doesn't really depend on what p and q are, but rather on the difference, p minus q. OK, so assuming this proposition, the pi part of the cohomology of the Shimura variety is pure, and that will imply that. So I guess I can say Vedeline representation, BC, P, Hj, Yst, X, LC. Here I should put 2n minus 2. And Frobenius semi-simplified is pure. And with a little bit of work, you get that RL of pi is also pure. Well, Vedeline representation and Frobenius semi-simplified. OK. So it remains to see how to prove this theorem and also this proposition, and also how to prove that the representation is tempered. So this, if we prove, I guess I think I denoted them A and B. So this would prove A, assuming B and C. And now I'm going to explain how to prove B and C. So this proposition and the fact that pi is tempered at the place P. OK, so in order to prove the proposition, we need to get our hands on that cohomology. And so that's the cohomology of a stratum. Each closed stratum can be written as a union of open strata, S prime containing S, T prime containing T. OK, and then in turn, these strata can be related to Igusa varieties. So we can relate the cohomology of Y0, S prime, T prime, LC to HC of an Igusa variety corresponding to H1, H2. H1 and H2 are exactly n minus cardinality of S, n minus cardinality of T prime. Okay, and so the problem becomes computing the cohomology of a tower of Igusa varieties. Except that we only, well, we're interested in the pi infinity part of it, and pi is a cuspidal automorphic representation. So we need to kind of, we're only interested in the stable part of the cohomology. And this can be computed in the same way as in Shin's paper on constructing Galois representations. So that's part 1 of Theorem 6.1 of Shin. So that's the theorem that computes the cohomology of Igusa varieties. Part 1 computes the stable part. Part 2 computes the endoscopic part. We're only interested in the stable part.
So in the stable part, that means in the sense of endoscopy?
Yes. Okay, and so in the end, kind of we relate this to whatever computation we have, and then there's some alternating sum to get this. In the end, we get something like the base change away from P of H, Y, S, T, Elk, C, pi 1 sigma is equal to pi away from infinity and P times some sum that depends on H1, H2, and some constant, again, depending on H1, H2. And then we're going to have something like red H1, H2 of pi P, where this pi P is such as the base change of IL pi P is isomorphic to pi 1 at P. So this is a regular P, just the prime P of Q. Okay, and this is a map on Grothendieck groups that's basically a composition of normalized Jacquet functors, Jacquet-Langlands map, and then it just picks out the Frobenius action from there. So this and we're really only looking at these as the representations of, well, or in the Grothendieck group of G of the finite adels away from P and cross Frob at F. Okay, so once we have a formula like this, we want to basically compute what this functor does, and this is done in a very similar way as the Taylor-Yoshida paper does it. So it's just a Taylor-Yoshida style computation of this functor. And we have, I guess, two cases when the representation pi at P is tempered or when it's not. So if pi at the prime P is tempered, then the computation together with the Weil conjectures imply the proposition C. And this is pretty much the same computation as in Taylor-Yoshida. If pi P is not tempered, well, then again we want to do that computation, but we need to do a little more. So let's take phi in the Weil group of K to be a lift of Frobenius. Then IL inverse ln k tensor 2 pi p shows up in the pi 1 infinity part of base change hx LC. So the way to see this is, for instance, you can combine the computation of Igusa cohomology with Mantovan's formula. And then you see that ln k tensor with itself shows up here. So from this, we know that whenever alpha and beta are eigenvalues of phi, in this representation, alpha beta squared is in Q to the z, where this Q is the cardinality of the residue field. Now, if we knew it for all alpha squared, so if we knew this for all alpha squared, then we would be done. That would imply that pi p is tempered. So the only other option is that for each alpha, the absolute value of alpha squared is in Q to a half plus c. Otherwise, pi p is tempered. Okay, and if that happens, then we can use a classification of irreducible generic preunitary representations of GLN of k to see that pi now, I guess pi pi, each of pi p1 and pi p2 have to be equal to the induction from some parabolic to GLN of some product pi1 times a character of the determinant, and we have to have power 1/4, and then pi1 character of the determinant to the minus 1/4 and cross times other terms which are of the same form for some pi2 and so on. So, and because we're in the case where we have an Iwahori fixed vector, this pi1 is just SP S1 of an unramified character. And similarly for the other factors. So again, we compute the red H1, H2 of pi at p, and this time this will introduce an error factor. So let me tell you what you get. BC away from P of H, Y, S, T. So this time, I mean in the Grothendieck group, we take pi1 sigma apart. We get C times a sum of V1, J1, J2 plus twice V2, J1, J2 plus V3, J1, J2. Each of these VK, J1, J2, are reciprocal. So each of them is the reciprocity of chi J1 inverse, chi J2 inverse, absolute value 1 minus n plus epsilon k. This is going to be the error factor. And times psi u, which comes from the GL1 part. So, and these chi's are characters such that maybe some pi ji is sp, sji, chi ji. So the fact that we have these error factors, well, if we look at weights, the weight of V1 will be an integer m minus 1. This will be an integer m, this will be an integer n plus 1. That's because the error factor will be either a half, minus a half, or 0. So C is a number. It's either positive or negative. And then we have the same, so positive coefficients for V1, 2V2, and V3. And they're all, so the weights are m minus 1, m plus 1. But on the other hand, on the other side, we have an alternating sum of cohomology. So the consecutive weights appear with different signs. So that gives a contradiction. So the left-hand side is an alternating sum, and the right-hand side has weights m minus 1, m plus 1 for some m. And C is either positive or negative. It's impossible for anything to cancel out. So we get a contradiction, which means pi p is tempered. All right. Yeah, I'm done. Sorry for overtime.